and I'm going to switch over to these slides. And I'm going to remind you of things that I told you, I talked about before, the basics of double categories. But really what I wanted to do today was to sort of gesture at some examples of double categories, particularly for sort of open C-sets, so things like open stock flow diagrams, open causal loop diagrams, etc. And then I wanted to just gesture at the bigger picture with double theories. And in order to do that, I have to say something about lax double functors, and this is not going to be the time where I go into those in detail. It looks overwhelming. It turns out, like normal with category theory, once you really study it, what seems initially scary or overwhelming or just a mass of symbols and weird things has a ton of structure, and it all makes sense, and it has to make sense, and it's beautifully well behaved and all that sort of stuff. But really what I wanted to do is gesture at the big picture here for double theories, because it's awesome. And it's at once familiar. It's a variant of something you've encountered before, C-sets. I think everyone here is quite comfortable with C-sets. But it takes C-sets to an entirely different level. Instead of mapping categories to sets, these disconnected elements, you map categories, a schema category, to categories. Instead of having tables that have a primary key and foreign keys, those tables are now categories. And just like the tables had foreign keys to other tables, now you have functors from one category to another. And so each of those categories can have its own internal structure. It could have, pre-orders, or it could capture, some sort of relationship with nesting from that from a pre-order perspective, or it could be monoidal, or it could be it could have some basic structure associated with capturing some variant of set-like behavior with more structure. So I want to talk about double theories, and I want you to know where we're going, so that when we come back and we do this lax double functors, you'll know it's worth it. And it's an awesome story, and it's an empowering story, and it's an implemented story, by goodness, in CatCoLab. Okay, CatCoLab has implemented this in a basic form. And it's because of that we can do things like find motifs in causal loop diagrams. We can reason about the compositional structure in causal loop diagrams, not treat just a causal loop diagram as having some set of links and that's all. We realize, any two end-to-end have a composite that's implied in the causal loop diagram. That all comes out of this, and it's gorgeous. So let's do this briefly. So together we saw double categories before, and the idea is that it's taking our notion of a category up a dimension. So now we have mappings from one morphism to another, and there's different stories here with two categories, which are a subtype of bicategory, which are a subtype of double category. And double categories give us these instead of these kind of globular mappings from a morphism to another morphism, they give us these cells, and there can be relaxed constraints associated with unitality and associated with associativity. And I know it seems weird, but I want to, imply it again and talk to you again. And when you hear it enough times, it's not going to seem so weird. Just like a normal category has objects and morphisms. There's a set of objects and a set of morphisms. Here we have a category of objects and a category of morphisms. C1 are the objects, and it's a category. So it has objects of that category. Those are objects. It has arrows of that category. Those are kind of the morphisms in this category. Okay. So our double category has, instead of having a set of objects, it has a category of objects and arrows between them that compose, have associativity, have identities on each object. And then instead of having a set of morphisms, you have a category of morphisms. And the objects in that are the pro-arrows, these horizontal arrows. So, those are these ones. These are the arrows in C0. These are the arrows in this category of objects, are these vertical arrows. The horizontal arrows, the pro arrows, are the objects here. And then the morphisms here are the double cells. They're these sort of things. Okay. And there's not automatically one of those for every frame, for every boundary here. No, it's certain boundaries have these things. A boundary is necessary, but it's not sufficient for there to be a double cell. But it's these double cells that have this kind of extra dimensionality to them, right? They can kind of map between things. And so so these are categories, C0, C1. And this category is related to this category. And how do we relate categories? You tell me, how do we relate categories? We have what between them? What is a structure-preserving relationship between categories? It's called a what? Functor. It's a functor. So there's a functor from this category of objects and arrows. Remember, instead of a set of objects, category of objects, right? There's a functor from this category to this one. It's a functor from this category to this. So it maps objects here to objects there. Objects here. What are objects in this category? You tell me. What are objects in this category? They are objects. They're just plain old objects. They're these things, right? Like that, right? Like that. They're these things. They're objects. So it maps objects here to objects here. What are objects in this category of arrows? What are the objects here? Does anyone remember?
Pro arrows.
Pro arrows. So they're these things. Okay. So this Y is telling what's the identity on an object here. Well, it's a pro arrow. It's an identity pro. It just goes from itself to itself. So every one of these objects is an identity pro arrow. From itself to itself. That's what this Y is. And this is a functor, so it maps morphisms to morphisms. What are morphisms in this category?
Vertical arrows.
Vertical arrows. So each of those is mapped to an arrow in this category. What are arrows in this category?
2 cells.
2 cells. So every vertical arrow is associated with an identity 2 cell where it's XW here, XW here, and this is an identity pro arrow. That's an identity pro arrow, right? And the double cell is the identity cell. It doesn't, sort of map. It's an identity relationship between the top and bottom. Now this source, what is this source? Well, it is a functor. It's a functor from this category to this one. What? And so a functor maps from objects to objects. What are objects in this category? EJ, you said it. What are objects in this category?
Pro arrows.
Pro arrows. Yeah, good. Good. Someone else spoke up. That's great. So it maps objects here, pro arrows, to objects here. What are objects here? They're these things, right?
Yes.
Yeah, so every pro arrow has a source object. Every pro arrow has a source object. And this functor, that makes sense, right? The source of this pro arrow is X. The target of this pro arrow will be Y, right? And you can reason about that, okay. But there's a functor. It maps not just objects to objects, but morphisms to morphisms. What are morphisms in this, or we could call them arrows in this category? What are they?
Two cells.
Yeah, they're two cells. Okay, so it maps a two cell here to a morphism in this category. What are morphisms in this category? You just said it earlier.
Regular morphisms.
Vertical arrows. Yeah, they're kind of regular morphisms. They're vertical arrows. So every two cell has a source and a target arrow, vertical arrow. This is the source, this is the target. Now, this is the codomain. Sorry, this is the domain, and this is the codomain of that. So it has a source and target, and it has a domain and a codomain of this double cell. Within each of these categories, you can compose. You can compose arrows like vertical arrows. If you have X to W and W to Z or W to A, you can end to end, you can compose them because they're in a category. You can compose double cells vertically because they're in a category. And those are strict, as Dürre-Pronk says, strict as can be. But then you have this structure here, which says, look, if you have two elements, two things in C1, say, two things in C1 joined by a single thing in C0. So suppose you have two pro arrows, those are the objects, pro arrows in C1, end to end, two of these guys end to end. Maybe it looks something like this. And they're joined by, they have share a common, the source, or the target of this one is the same as the source of that one. So they look like this end to end. Then we can compose them and get another arrow in C1. What's an arrow in C1? Who can remember? What's an arrow? Well, sorry. We'll do it first for this. That's what I meant to do it for these pro arrows. Don't pay attention to me using this diagram. It's these ones here, these pro arrows. If these are objects, pro arrow and pro arrow joined by an object in C0. What's an object in C0? What's
An object.
An object. So they're end to end joined by the same object. Target of this one is the same as the source of that one. You know, so like a pullback or sort of target source. Then you get an object in C. What's an object in C1? So pro arrow. This is a functor that puts those together. And similarly for arrows in these, you get an arrow here. What's an arrow in C1? It's a square. It's a square. It's a square. It's one of these things. It's a two cell. So if you have two cells, this one and this one, and they're joined together, source of this is the target. Source of this is the target of that. What is an arrow? They're joined together by an arrow in C0. What's an arrow in C0? What's an arrow in this category over here? Over here. What's an arrow?
Regular arrow.
Regular arrow. So you have these two cells and they're joined by regular arrow, right? Target of this one, source of this one. You get an arrow. You get an arrow in C1, which is a two cell. So this one down here is pro arrow composition. This one is composition of squares. Okay.
Can I ask a question?
Yeah.
Can you go back to the slide that has the picture of the two cell on it?
This one?
Yeah, that one. Yeah. So, okay. So if you're mapping from C1, you're mapping a morphism in C1, which is a
Yeah.
2-cell like this, to a morphism in C0. Could you say, like, for this alpha here, which would it get mapped to F or G in
So
C0?
the source, this is one functor called source. This is another functor for target. Source functor will map objects here to objects here. You're comfortable with that, I think. Pro arrows to the source, like the source object. But it will map 2 cells. That's what you're asking about, to the source arrow. So morphism here, right? Maps morphism to morphism.
Oh, okay, I see.
And so this would be the source. Yeah.
That is source would map F, and then target would map G.
Yeah, source would map alpha here, the arrow in the double cell, the arrow, which is a double cell in C1. It would map that to the arrow, the source, the F, and it would map target would map alpha to G. That's the target of alpha. Is that helpful? Yeah.
Yeah, thank you.
Okay. Now it turns out there's so these functors here are not on the nose with respect to associativity and with respect to unitality. And what this means, a fancy term, but basically they're not exactly associative. Just like in Haskell, right? If we have A comma B as a pair, and then within a bigger pair, that and C, it's not exactly the same type as A comma B comma C as a pair. It's not the same, but it's isomorphic. It's the same information. You can go back and forth losslessly. There's an isomorphism between them. That's what you have here. This is not exactly associative on the nose, but it's isomorphic. There's an isomorphism between them. And similarly, this isn't guaranteed to be unital on the nose. So in other words, if you have Y, like if you have the unit pro arrow here, and you compose it with another pro arrow, and that's end to end with it, it doesn't necessarily give exactly that other arrow, the other pro arrow, but it gives something isomorphic to it. So this is as I understand it, a sort of weak or a pseudo. Yeah, it's a pseudo category. It's not exactly on the nose, but sometimes this is strict, and sometimes these are both strict. Sort of a strict double category. Otherwise, I think it's called variously a weak or a strong but basically it's not strict. It's not where these equal this. If it were exactly associative, this going this way, like taking the product of, like taking the composition of these and then composing with this would be the same as taking the composition of those and composing with that. And it's not exactly that in general for a weak and strong, and well, weak or strong, whatever you want to call it. It's not exactly the same, but it's isomorphic. Whereas for a strict, it'll be isomorphic. And for strict, this would be isomorphic. And I guess Doretta comments that for a normalized thing called a normalized one, these are identities. So like composing with a identity isn't, it gives exactly that thing. Okay, so it bears noting for each object, for each kind of object in here, you have an identity arrow. That's one of these that goes from itself to itself. It's, be like going from X to X, right? It's an identity arrow. But there's also a separate identity pro arrow from it to itself. And that isn't necessarily unital. So if you that one composed with any other pro arrow from from X doesn't necessarily give exactly that other arrow when it's composed with it. This is a functor here. This is a functor, and it performs kind of composition that's not quite associative on the nose and not quite unal on the nose in general for weak and or weak / strong. So this cell, I commented this last time, but it's worth emphasizing, like whether or not this cell exists and what it is depends on the particular morphism here. The particular morphism here you're talking about. It's not just a whole Hom set here and a whole Hom set. No, it's a particular morphism, so particular pro arrow, particular arrow, that will determine whether or not it exists or not and what it is. Sometimes it's a question, does it exist or not? That would be called a flat or a thin double category. Sometimes it's which one is it? Two sets are not always mappings. I think some of them are mappings, but sometimes they're not mappings. They just say like this is compatible with that. It's the same relation as that. Or it's a homomorphic relation or something like that. And the rules for like whether or not like what a two cell means are very different between categories. Okay. And a given frame, one of these could have more than one two cell. There could be more than one associated with the frame. So I asked John if this frame is a mapping. He said, don't think of it as a mapping. He said, it's a frame and inside it is a picture of George Washington. Just thought I'd relate that. Okay, so we have composition within these categories. Within these categories, we can compose these arrows normally. Within this category, these squares, these double cells, they compose vertically. These arrows compose vertically. They're the vertical arrows. That's all normal. That's all strict, etc. It's really this horizontal one where you have kind of a bit of looseness with respect to associativity, bit of looseness with respect to unitality, like whether you combine a morphism with an identity, does it give exactly that morphism, does it preserve exactly that morphism? But you have these sort of nice little source and target. So this unpacks it a little bit, and you could see, what you get when you compose squares, and what the source of a square is. It's an arrow in this, which is a vertical arrow. The target of a square as well, it's a vertical arrow, right? And then these arrows within this category, they have a source and target internal to that category, right? Every arrow has a codomain, I guess I should say codomain and a domain. And there, every object in here has a identity. So you have this nice kind of structure. And I was saying that associativity is not guaranteed to be up. It's not on the nose, as category theorists like to say it. It's not strict, but there's a invertible isomorphism here. So there's it's invertible. So you can go from this and this to this and this, just like you can go from pair of AB, comma C, that outer pair, to a pair of A and pair of BC. You can go between them. The same information, just packaged in a different way. And here again, H composed with identity pro arrow is not necessarily the same as H, but there's an invertible mapping between them. Okay. I would love to cover this, but time is precious, and I want to get to this other components. There's a beautiful story here. And basically, look, these double categories are really nicely behaved. You do nice things with them. Their freedom is constrained, so they behave beautifully, and they give you sensible things, and they give you, they behave tractably and nicely. And you can simplify things in different ways. So an example would be this interchange law. If you have 4 squares, 4 double cells, you can either do, alpha and beta here, and then beta after alpha, composed vertically with gamma after delta, delta after gamma, using this external composition, this horizontal composition, this way. If you compose vertically, then it's the same as doing gamma vertically composed with beta, and horizontally composed with gamma after alpha. So look, they're really nice. Now, there's a set of beautiful examples for this, and they're awesome, and they're everywhere. You see these things all around. It's incredibly awesome. I want to cover these in more detail in a later time. I'll just note, like, these could be relations. So this is a set. This is a set. This is a relation between sets. Relations compose. If A is related to B and B is related to C, A is related to C, right? These are functions. So these are relations to pro-arrows. These are functions. And this is a relation. And a square exists if and only if it's thin. It's called flat also. So a cell exists if you have S and T and R, then if U of S, so that's hitting this element of S, these are sets, this element of S, if we hit it with U and we hit this one, if we have an element of T called Lidocus T, we hit it with V. If that is in R prime, if these two relations are in some sense compatible, given U and V, kind of they're related through U and V. Systematically, you apply U and V correspondingly here, and you get R prime. Then there's a square like this. That's kind of a compatible, right? They're compatible relations. They're basically kind of almost, I think, of the most homomorphic, although I could be criticized for that. But they're, like from this you can get this using U and V. And so, and I'll come back to this. There's another one that's important, which is span. Objects, so span of a category C, objects are objects of C. Arrows, vertical arrows, are arrows in category C. So this is a category. These are objects in C. Vertical arrows are morphisms in C, arrows in C. Pro-arrows are spans like this. Now you might say, like, what the heck is that? Well, look, this is an object in C, and this is a morphism in C. You can imagine spans in this, right? So this is a span like this, and if this is a commuting square, so this is a push out, and that's a pullback, and this is a pullback. Then there's a 2-cell here between S prime and T prime. There's a 2-cell. And there's a 2-cell between S and T, S prime and T prime, with U and V, and with these along here. If this is commuting, if you have these two kind of pullbacks here, these are pullback squares, in case you didn't notice. Or they're like pullback squares. I think they are pullback squares, but anyway, if this is a commuting, these are commuting, and it turns out this reduces to monoidal categories, and we'll come back to that. This is kind of interesting. Okay, look, there's one called square of C. Okay, so objects are objects of C. Great. Vertical arrows are morphisms from C. Okay. Pro-arrows are also morphisms from C. That's kind of funky. And there's an identity, there's a 2-cell in a given frame if the square commutes. So if you go this way, remember these are just morphisms. Pro arrows are morphisms, vertical arrows are morphisms, and C. If this commutes, there's a two cell, and otherwise it's kind of funky. Yeah. Okay, this is the one closest to my heart. All right, this is our cospan category, right? Okay, in our cospan category, we have this left adjoint. Some of you know the story for this. This is the feet category. This is the apex category. And an object here is an object of A in this double category. A vertical morphism, don't look at this right now. Objects are objects of A. Vertical morphisms are morphisms of A. Horizontal morphisms are structured cospans of this form. Okay, so like a horizontal one cell, that's what this means, is this. The objects in this double category are from A, but there exists a pro arrow between them if you have this sort of form. And I think that's fair to say. And a two-morphism is a commuting diagram of this sort. So in other words, here we have structured cospans as the pro arrows. We have vertical morphisms between A, which map from feet to feet, feet to feet. These are cospans where this apex is an X, right? If this is a commuting diagram, then there's this two morphism, in which case we have kind of I think it's like a homomorphism between structured cospans. So this would be kind of a homomorphism from the apex to the apex, such that you could go to this apex and then down and be the same as kind of mapping down to this and then going over to this one. And same thing here. So here, this is not a equivalence class of structured cospans. It's just a single structured cospan, by goodness. This is a single structured cospan. These are going to be homomorphisms between these things. And the general picture here is a unification of the world of open C-sets. You imagine the structured cospan being an open stock flow diagram. And then having homomorphisms between stock flow diagrams. That's what this H is, in between their feet, for these interfaces between them, these kind of interfaces to the stock flow diagram. But this is a homomorphism. So now you have, in a single category, homomorphisms between stock flow diagrams and open stock flow diagrams that can be composed end to end, right? You have one of these, you have another one here horizontally, and through this nice thing here, you can compose them, right? Through this nice thing here, you can compose those together, and you can compose, in fact, these things here in a way that also compose horizontally. Okay. Okay, now I just want to give a glimpse of where we're going, and like you'll wonder, why am I so excited about this? Like it may seem like some arbitrary sort of factoids and categories here, but look, here's the deal. Here's the new reality for CatCoLab. Look, we used to have schema categories, right? That encode for us a kind of theory. We're going to now have strict double categories, okay? Double categories. Not just a regular category for schema, but a double category. Okay, that's kind of interesting. Now, before, we used to have a functor which mapped that schema category into set, right? And that would give us a C set. give us a specific stock flow diagram, or give us a specific, causal loop diagram, right? Now we're going to have a lax double functor from T into span. Now, this is a double category. This is a double functor. And what this is going to mean, what this gives you is actually a category. So instead of mapping to set, you're mapping to a category, where each object of this category, of the schema category, turns into a category, of the schema double category turns into a category. And each morphism in the schema double category turns into a functor between those categories. So instead of just being disconnected primary key elements of these tables that you map into, you're mapping into connected objects within this category. So instead of having a C set, you have a C category, where each object is a separate category. Each morphism between those objects turns into a functor between those categories. And you can have morphisms between these models, just like before we had homomorphisms between C sets. You can have morphisms here between these C categories. Okay. And then there's higher levels of structure, which I don't fully grasp. Now, this may seem like wacko, but it turns out that if you deal with these lax double functors, we're going to be working to understand them. They've got some extra bells and whistles, and they have really nice behavior. But if we have them, basically, these lax functors, these lax double functors, from a category into, and it's no longer set, it's into span. And for each object in this, you get a category. It encodes a category. Each object here gets turned not into a set, like before, right? When we had a stock flow diagram, we have an object in our schema category for variable, right? It gets mapped over to a set of variables. Remember that with C sets, right? Each object gets mapped to a set. You surely remember that, right? If you had an object for links, if we had an object for vertices in a graph, it gets mapped to a set of vertices. Object in our schema category for edges in the graph gets mapped to a set of edges, right? And morphisms between E and V in the schema category get set into a foreign key from the E table. For each element of the set of E, you have a mapping, you have this function which says for that element where it goes to in the vertex, what its source is, what its target is. Now, instead, for each object here, we get a category. And we have objects in the category, and we have morphisms. And we have ability to compose and identities in this category. And you could be excused for saying, oh my God, this is so complex. But look, it just gives you a category. So instead of having a set for each object here, or a set of edges, a set of vertices, now we have a category of edges, a category of vertices. And that is extra structure. That can do extra things. And for causal loop diagrams, amongst other things. Now, if the fact that we have a set, not just a set of links in our C set, but now because we have a C category, we have a category of links. What can we do with a category we can't do with a set? What can we do? We can what? What can we do with a category? What can morphisms do in a category? They can, begins with C, ends with E.
Compose?
They can compose. They can compose. So we can compose our links in our causal loop diagram because we have a category of this encoding the causal loop diagram. It's awesome. We can compose these things. So now we have not just a causal loop diagram with some given links that sit there like bumps on a log, you know, A to B and B to C, just telling us what's in that closed loop diagram. That's interesting. It's beautiful. That's great. But what we really want to do is we want to recognize that if we have one from A to B and one from B to C, there's an implied one from A to C, right? We want to be able to compose them and recognize, oh, there's a negative feedback loop there. There's a positive feedback loop. No matter how many links we have, we know that there's there. And that's what we can do with these categories. But get this. Get this. Take a load of this. It's not just that. Not just objects here get turned into a category. That's cool. But arrows here in this category. Remember, we used to have C sets, right? And we would have an arrow, a morphism from like E to V, right? Source says for each, for object E in our schema category for graphs, there's a morphism to object V in the schema category. I think you're comfortable with that. And there's another one for target, right? Here, if we have an arrow in this double category, an arrow, one of those vertical things in this double category, that maps over. So these objects in D map to a category. These vertical arrows map into functors between those categories. So before we had, you remember, like a table of edges? Do you remember that? A table of edges? Different possible values of the set, right? The set of edges. And for each such set, we had a foreign key that tells us what it maps to over in the vertex table. Remember that? And this reflects the fact we have the source morphism in the schema category mapped to a source function, the map from the set of edges to the set of vertices. You'll surely remember this. Now, we don't have just a set of edges. We have a category of edges. We don't just have a set of vertices. We have a category of vertices. And now we have a functor between these categories. And that functor can do neat things. That functor honors composition when it maps. It's a structure preserving mapping between those categories. It honors composition. It honors identity. And we have these functors between these categories that come from this. So each object in D gives a category. Each morphism in D gives a functor. And those functors can go between those categories. And each cell in D, remember D is a double category. Each pro arrow in D gives a natural transformation. Each cell, yes, in D gives a natural transformation that applies between the corresponding functors. I think at source and target functor probably. I'd have to unpack that a bit. But not only that, we have pro arrows. We have pro arrows in D, right? We have pro arrows here. We don't just have objects mapping to categories. We don't just have vertical morphisms, which map to functors between categories. We don't just have cells, as neat as those are, which map to natural transformations. No, we have pro arrows as well in this, right? Pro arrows, horizontal arrows, right? And for each pro arrow in D, we get a pro functor. You may wonder where the pro and the pro arrow came from. Well, the pro functor. Pro arrows turn into pro functors in this set of categories we get out. So we have objects go into categories. So category of edges, category of vertices. Morphisms in schema category D turn into functors between those categories. Cells in the schema category turn into natural transformations. And pro arrows in the schema category turn into pro functors between categories. Between category D, C, and category D. And I know many of you are innocent of pro functors, and I promise I'll give an introduction to profunctors, but profunctors provide an extra level of flexibility to mapping between structure preserving mapping between categories. And I'll just highlight that sort of like with relations kind of have a relaxed feel to them compared to functions. Right? You can have functions between two sets, but a relation between two sets is more flexible, right? A function says if for every element here, it has to map to an element over there, but only to one element over here. But a relation could take, for a given element here, it can map to 0, or it could map it to multiple, right? It's kind of a more relaxed version. And a profunctor, I think of as kind of like a somewhat more relaxed version of a functor. It's also a bridge between two categories, and is kind of pre-composition and post-composition. So where's this all going? Well, look, by encoding these things as categories, we get the advantage of extra structure. We can reason about composition. And this is what CatCoLab does. And CatCoLab has basically implemented a fair bit of this already. Now, why? Well, there's many reasons why. One is to capture this stuff with open stock flow diagrams, open causal loop diagrams, open systems, which are first and foremost systems, pro-arrows. Those are objects in C1. But they also have these kind of interfaces here. And we can reason about that alongside reasoning about homomorphisms, these structure preserving mappings. Alongside, we can reason about those as mappings, as other types of morphisms, vertical morphisms between these systems. So we have this ability to reason about sticking them together with structured cospans. We have this ability to reason about homomorphisms between them, two types of kind of morphisms. And that's nice. But it's also this other thing I mentioned, that because we have categories, we can capture compositional structure. And so we can enliven, we can empower, we can capture the fact that our causal loop diagrams have a compositional structure to them that links can compose. Instead of being kind of these static objects, we can reason about the compositionality if we wish to do so. We can, amongst other things, find through simple mappings all negative feedback loops in our causal loop diagram, regardless of whether it's a single loop, a single variable with a loop to itself that's of negative polarity, or whether it's a minus, A to B that's minus, B to C that's minus, and C to A that's plus. And any combination, it could be an arbitrarily large loop, and we can find it because we can reason about the compositional structure of our systems by in this context, because we're mapping to these categories, and we have functors, and we can have a functor into the sign category, or Z sub 2, which captures modulo. These are some reasons for capturing this. Double categories give us much additional freedom. And here we're dealing with double theories. And this is where Topos is putting their big bet here, is going beyond standard theories where we have a presentation of a category, we map it into a set, beautiful as that is, powerful as that is, homomorphisms between instances of two graphs, or homomorphism between two stock flow diagrams, homomorphism causal loop diagrams. Powerful as that is, here we can do something much richer yet. We have these double theories. We can capture a lot of additional richness, capture a lot of compositional reasoning, capture these open systems. And a key to this that I'm trying to motivate, because I know it's going to take some pain. You've already been through this pain of learning about double categories, and I know it's not that pleasant, particularly when we start talking about things like functoriality. But the truth is, if we can just get on lax double functors and understand how they preserve the structure of these categories, like mapping D to span, that will help us understand why an object maps to a category, why an arrow in D maps to a functor, a vertical arrow, why a cell maps to a natural transformation between categories, between functors, and why pro arrows map to in D map to pro functors between the corresponding categories. So this is enacted in Cat Colab. I can walk you through the Cat Colab code bases where it uses these facts, where it uses this to create a category. We specify from a single object. We can specify with a lax functor, the appropriately judiciously chosen lax functor. We get out a category. And from a pro arrow in it, we get out a pro functor, and those two allow us this power to reason about compositional structure in our causal loop diagrams. And it's right there in the Cat Colab code base in a generic form that applies not just to causal loop diagrams, but we could apply it to many other categories, including stock flow, etc. So this is our future. This is our destiny. And we can rise to the occasion in order to have this extra flexibility of double category that double categories afford us. This flexibility to reason about compositional structure, flexibility to reason about open systems, and other benefits yet unplumbed. So this lies ahead. We have a bit more pushing to do to understand exactly this lax double functor. This is a double functor. By the way, this is a normal category, not a double category that objects get mapped in. So one thing I might do next time to further motivate this is walk you through the Cat Colab code base, and you'll see how this is used and how this is used and how it gives us this beautiful ability to reason about compositional structure for causal loop diagrams and find all reinforcing feedbacks in a causal loop diagram, no matter how big or small they may be. Find all negative feedback loops, etc. I'll show you how that's captured in code. And then maybe we'll take on the challenge of reasoning about these lax double functors. I'll just say one word about them. Lax double functors, if you have a double category. Do you remember in a double category? One of these ways of composing, either horizontal or vertically, is strict. Do you remember which it is? Which of them, composing vertically or horizontally, which of those is strict? Who can say? Vertically is strict. Vertically is just within each of these categories, within C0, you have the ability to compose arrows. That's right. You have the ability to compose, these are just morphisms in this category. You have the ability to compose them vertically. Horizontal composition is loose. Is loose. Is not strict. In general, it's weak or strong. Horizontal, and basically these lax double functors, they map double categories to double categories in ways that are strict in the strict direction, the vertical direction. They preserve composition in the vertical direction. You can either have morphism F and morphism G, compose them in the source category, and then map over with the lax double functor, into the target category, or you can map F over to the target with the double functor, G over, with the map it over, and then compose in the target, and you get exactly the same thing. But lax double functors compose in the horizontal direction laxly, loosely, reflecting the kind of loose composition horizontally where it's not associative up to the nose, on the nose, it's associative with some give, and where it's not unital on the nose, typically it's unital with some give. Here you have it lax, you have composition preserved laxly in the horizontal direction. And there's a thing called a laxator and a uniter, which reflect it. Okay, so that's all for today. I've tried to give you the big picture while reminding you of these double categories that are our future. These things take time to sink in. And I appreciate your attention. And, I really think this is going to be worth it. And maybe because we'll see the code next time, you'll realize just how relevant this is to the wonderful functionality being exposed in Cat Collab in Rust. Thank you very much.
Sorry.
Yes.
Hi.
Nona. Hi.
Hi. Sorry for bothering you.
No.
Can you please send me the link of this video?